Thank you so much. So I'm really excited about this talk because this is a technical deep dive. Usually when we talk about GDS, we just say like, oh, there's so many amazing things. It's so powerful. And we just list them off and we don't really spend a lot of time. So this talk is all about how to do link prediction in Neo4j. So how to train a link prediction model, what can go wrong, what you should be thinking about, kind of the ins and outs of what I think is a really cool application of graph. So I'm going to be covering the slides and Jakob is going to be doing a live demo to show us how it's really done. And so before we get into link prediction, I always like to kind of level set to make sure that we're all talking about the same things. So you've probably seen me present this slide before. When we talk about graphs in data science, really it could be anything from queries for analytics, feature engineering, data exploration, to machine learning where you're running algorithms and making predictions, to visualization where you're exploring your data, you're collaborating, you're explaining your results. And really, when we talk about graph data science, what we're really talking about is answering questions with relationships. However, Jakob and I both work on the graph data science library, which is the machine learning part of Neo4j. And if we kind of step back and talk about like what is machine learning, how does it break down, we're all familiar with, you have your unsupervised machine learning, which is really driven by the data where you're looking for patterns, trends, anomalies. There's too much to look at. What's most important? What looks like other things? Or you're talking about supervised machine learning, where you've got labels and you're training a model to predict a category or a value. And so in Neo4j, what that really means is the graph algorithms are our unsupervised ML. Those are the things we've talked about for the last few years, community detection for clustering, similarity for association, embeddings for dimensionality reduction. What's new, and really we've been spending really the last 6 months really working on building out these capabilities, are supervised machine learning. So how can I take the labels that I have in my graph and make predictions? And when we talk about supervised ML, we're really talking about kind of two things. One of those things being predictions that are influenced by your graph structure. And this is really that better together story where we say, you've got data, there are connections between your data points. You should load it into a graph, run graph algorithms or graph embeddings to describe important features of your graph, add those back into your tabular format, go train your model, and it's more accurate. And that's really, you can get better predictions with the data you already have. The other thing you can do, though, is you can make predictions about the structure of your graph. So graphy stuff in the graph. You can enhance your graph data, your connected data, by predicting missing data or the changes that are going to occur in your graph in the future. So this might be, predicting node labels. So I want to do node classification. I've got some nodes that are labeled. I've got some nodes that aren't labeled. I want to predict the labels of those unlabeled nodes. Or I want to predict maybe a node's label is going to change in the future. Or maybe I want to predict what relationships are going to form or what relationships are missing. And this is really predictions about the structure of your graph and either completing missing information or enriching it with predictions about the future. And that's what we're going to focus on here. And so when we talk about what you can do with in-graph machine learning at Neo4j, what is your input? What is your labeled data? And it's really your graph. It's your Neo4j database, your in-memory graph, is your labeled data. The relationships between your nodes or the relationships that don't exist, those are labels of here's a link, here's not a link. Or, you have node labels. This person is innocent, this person is a fraudster. This customer is a happy customer, this customer is a churn risk. So your graph itself provides the labeled data. And your features that you're training on might be pre-existing attributes that you loaded into your graph when you built it. Maybe you have people and you're doing link prediction. Maybe you have something like age of person and that was there before. Could be the results of your algorithm. So using those unsupervised machine learning techniques to describe your graph. So maybe you run an algorithm like PageRank to give each node an importance score, or you run graph embeddings to describe your graph in kind of a machine readable way. And basically, these create the features that you're going to use to predict your labels. And what you can do is either node classification. So what kind of node is this? I have innocent people and I have fraudsters. I want to predict who out of my unlabeled people is going to commit fraud or who's going to churn. Or for link prediction, maybe what you're looking at is it's really, is there an edge between these two nodes? Um, and I want to predict either where edges are going to form in the future or where are edges that I just haven't observed, but they already exist. And that's kind of what we're talking about when we talk about in-graph ML. And if we focus on link prediction, what is it good for? And I think once you start thinking about link prediction, kind of everything becomes a link prediction problem. So you might have seen the slide in terms of like, what are graphs good for? Really, if graphs are good for something, link prediction is useful too. So if we start off with kind of the easy case of social networks, like Emil talked about in his demo, I've got a social network, I've got people who know each other. I want to recommend a friend for someone that they're going to like. Or maybe it's a criminal graph, and I want to predict who's going to form a criminal association next. It's about predicting either unobserved relationships or future relationships. If we talk about our classic recommendation use case where you have, people buying items, viewing items, returning items, what does link prediction do there then? Well, you can predict what someone will buy next for a recommendation. So you can predict future edges between people and items. Or, we talk about knowledge graphs, right? Where you have heterogeneous concepts. You have, in my example here, genes, chemicals, diseases, symptoms. Link prediction in a knowledge graph is really about filling in the missing relationships in your data set. So maybe I have this drug binds this gene's associated with this disease, which causes this symptom. I could predict this gene causes this disease, right? So it's all about filling in the missing data. So really, whenever you've got a graph, link prediction probably is useful. This is kind of the slide we usually use to talk about link prediction in Neo4j, where we tell you Neo does all the hard stuff. So if link prediction is just prediction of unobserved edges and the relationships that'll form in the future, what you need to do in Neo is you load your in-memory graph with the nodes that you want to make predictions on and the features you want to use. Split your graph into a test and train graph with our split relationships procedure, and then use link prediction.train. And what we do internally is you give us a whole bunch of parameters to search. We'll evaluate the accuracy of all of the models. We'll build a bunch of models. We'll return the best performing model. And then that's in your model catalog. You can apply it to new or unseen data and start making predictions about where relationships belong. And since we're using logistic regression, you get a probability score. How confident are we in that prediction? Sounds super easy, right? Well, we're going to be talking for a while more, but the bottom line is building a great model is a little bit more complicated. There's a lot of questions you need to think about in order to get it right. And so that's what this talk is really about. So what's so hard about link prediction? I'd really start with understanding the problem. So as I was talking, you heard me talk about both filling in missing relationships and predicting new ones. Both of those are different questions that you're trying to answer. And they're really two different problems that you would handle in two different ways. So when you do link prediction, you really want to start off with, what am I doing? What am I trying to predict here? Then you want to think about data leakage in your test train split. So how do you split your data into a test graph and a train graph? How does that impact your connected features? And how do you prevent kind of information about your test data from leaking into your train data? And I'll explain why that's tricky. Then a big issue is imbalanced data. If you think about a graph and you say, a positive edge is an edge that exists and a negative edge is an edge that doesn't exist. There are way more negative edges in your graph than positive edges. So what do? How do you pick negative examples in the first place? Maybe you want to resample, but that's going to distort your distribution. What's the right performance metric to measure accuracy here? And what's a good score even mean? And finally, you're like, cool, I figured all those things out. I'm ready to go. There's kind of this footnote that performance is tricky with link prediction because you're training embeddings on connected data. You need to fit a model to all of these potential pairs, right? I said, you've got every relationship in your graph that exists, and every relationship that doesn't exist is a negative example. And then when you're making predictions about what's going to form next, you're basically applying that model to every pair of nodes in your graph. So it's computationally expensive, and that's something to think about. So let's start off with defining your problem. There's really two problems here. One is graph completion, where you're filling in missing links. This assumes that you have incomplete data. There are relationships that exist that you just haven't observed, and you need to recover the missing edges. And here, when you look at splitting your data, this is going to require random splits. So you may be able to retrain your model on the full graph to improve performance, but splitting gets a little trickier, and we'll talk about that next. And then evaluating your data is hard because what is your natural holdout set? Do I randomly split my graph? Is there some logic derived from the domain model that tells me how to split my graph? This is something you really need to think about for the problem you're trying to solve. The other use case of your time variable graph, where you're predicting the future, is a little easier. This is basically you have relationships that have timestamps, and you assume that you have an evolving graph, and you're going to predict what will happen next. So in my little figure, I have a person bought an item. What will a person buy in the future? This makes splitting your data intuitively a little easier, right? You've got timestamps on your relationships. You can time slice your data and create a holdout set from the future. Evaluation becomes easier because your holdout set makes sense, but you need to think about how far in the future should my holdout be? Should I split it, the last 5 years and then everything before that? Am I doing 1 year in the future? You need to think about that. And you need to confront, what if assumptions change? So 2020 broke kind of everyone's models. If you were doing time slicing and you had, up to 2019 and then 2020, that wouldn't be very performant, right? You have to think about, do assumptions change? Do distributions change? Really, it's about understanding the problem at hand. So let's assume you've done that. Your next hurdle is data leakage, and how do you split your graph? And so data leakage happens when information from outside your training set is used to create your model. You're basically cheating by looking at the answer. And so for link prediction, you're usually training by looking at connected features, which may accidentally bleed data from your test set. So if you think about it, if I want to create a graph embedding, that graph embedding is going to capture not just my node of interest, but it's going to capture the topology of the graph around that embedding. So if the graph around that embedding is outside of my train set, that's a problem. Or even if I do something simple like PageRank, PageRank is still calculated based on the connections of that node and the connections of those connections. And if you're mixing them between your test and train set, you're going to get into trouble. So let's talk about different approaches. One that data scientists often start with is, okay, my graph is really a table, right? Each node is a row, features are columns. I'm just going to generate my connected features and randomly split. This is really problematic, right? Because if you look at my graph, I've got my gray nodes and my blue nodes. If I randomly split it, I'm going to have leakage from my test set into my train set because of those connected features. So I might end up with a really performant model that then sucks when I try to apply it to real world data. So what else can you do? You can look at splitting your data first and then generating your connected features. So I've got my two subgraphs, and then I'm going to generate connected features within those subgraphs. So I'm not sneaking a peek at the answer. Or for kind of our time variant model, you might be lucky and you have timestamps. So here's my same graph. I assume that there is a year on each relationship. What I can do here is I end up creating my train graph, which is everything before 2004, and my test graph, which is everything that happened next. It's the full graph. And this intuitively makes a lot of sense. But again, you need to think about, where does that time slice happen? Do things become stale? Do my assumptions change? One note about connected feature engineering, and Jakob is going to show this later, is usually we're talking about node properties, embeddings, algorithms as input features. But you can also use connected features. So in link prediction, we support linked feature combiners, which for each pair of nodes that you're training on that are connected or not connected, we can generate these combined features based on the pair. Using Hadamard, cosine, or L2 norm, you basically create features that describe the combined pair of source and target. So that's really powerful. Cool, so negative samples. Link prediction requires both positive and negative samples. We talked about this. You have your relationships that exist and your relationships that don't. But you need to decide how to define them and how to measure them. So if we just start off with every non-connected pair of nodes is a negative relationship, you end up with a really noisy and dense graph. So if it's basically, quadratic complexity. If I just have one node, even in my toy graph, and it has one positive relationship, it has a negative relationship to every other node in the graph. So this is probably not what we want to start off with. Our split relationships procedure lets you specify a negative sampling ratio. So how many negative relationships should I create for every positive one? And this is, again, you are distorting the distribution of relationships in your graph, but it's a great way to kind of rebalance your data. What you can also do is define your own rules for negative relationships and create them in Cypher. So maybe I'm a domain expert, and I know that if a node isn't connected to another node at least 5 hops out, it's never going to be connected. I can manually create my negative relationships based on that rule. It all comes down to what's important. And then remember, we've got really imbalanced data. So if most of your links are negative, we could train a model that's amazing, it's 99% accurate, and it says no links will ever form, and that would be fine. But instead, what we use for measuring your model performance is the area under your precision recall curve, which is much more sensitive to those false negatives. So really, it's about thinking about your problem and what you're trying to solve. You can also use negative class weight to determine the impact of those false positives. How important are they? Do you care more about false positives or false negatives? And so finally, link prediction is really computationally intensive. So just remember, when you're running it, you're going to be spending a lot of time training your model, creating negative samples, and when you're making predictions, evaluating every potential pair of nodes and their features. So it takes a while. And with that, we're going to toggle over to Jakob presenting a hands-on demo of what this actually looks like for 2 data sets, Quora, which is a citation graph, and a social network, which has time-variant data. And if you're curious, this is up on GitHub. And so Jakob will show you how it's done.
Thanks everyone for joining. Glad you are interested. So today we have 2 demos. One is about a set called Quora, which is a set of papers actually relating to machine learning, and this is a famous benchmark data set on which people do link prediction. So this set contains about 2,700 papers, and each paper has some features which are actually words that appeared in the paper. And then the structure of the graph is that you can tell which papers cited each other. So the link prediction problem will be to, given a subset of papers and citation links, we want to predict what other papers are citing each other. So this database has been loaded with a relevant data set, and the first thing we do is that we use a GDS procedure to create a graph, which we will call here Quora. And the first argument here is the node label of the nodes that we want to load. And we also give a relationship projection, which creates these citation relationships. And we make the graph undirected. And the data already is populated with vectors, which are called features. I think there are, if I remember, 1,400 binary features. So let's run that. And here we see that the graph was indeed created, and here are the exact node counts and relationship counts. So the first thing we have to do after that is to create a test set. And that we can do with another dedicated procedure, which is called split relationships. And what this does is we have to choose a name for the relationship type that is created, which will contain the generated relationships, in this case, the test set. This contains both a sample of positive relationships, and in fact, it's 10% because we set the holdout fraction to 0.1. And at the same time, the negative sampling ratio of 1 here means that we'll get as many negative randomly sampled relationships in the test set. And we also get the second output, which is, we call it here, the outer train set. And that contains everything which was not sampled in the test set. And that's useful because we want to create a training set out of that, and also a so-called feature network, which we can give as input to an embedding algorithm, as we soon shall see. So let's see, have I run this? It looks like it. So next step, it's very similar, and that will create the train set. So And what is remaining here, so now we took 10% of what was remaining in the previous step, which is the outer train set. That is the filter we apply. So we are basically taking this as an input, and we get two outputs. We get the train set with generated relationships, positive and negative ones, and what's remaining is now the so-called embedding graph here. So now we are finally ready to run our embedding algorithm. And the embedding algorithm of our choice here is called fast random projection, or fast RP. And this is a very scalable algorithm, actually finished here in only 53 milliseconds. And we used, as we said, why is this not here? Now it's here. So we used the embedding graph as input. So this guarantees what Alicia spoke about earlier, to not leak data. We are not using any relationships from the test set or the train set. And we can choose what we call the property, which we generate now, which contains the embedding vector for each node. We call it FRP. The length of each vector assigned to the nodes is here 512. This is actually a kind of tweak of fast RP. So half of this vector will contain special features which also look at the node properties of the graph. So this captures both node properties and graph structure. And the input was the raw features, which were basically the words of text in the papers. So we have our embedding. And the next step, we are actually going to do the link prediction. Yay. So I'm gonna run this and a drum roll, and we'll talk about what are I think it finished, by the way. Yes, it did. So let's just explain a little bit how we set this up. So first of all, we need to provide what is the name of relationship type in the graph, which contains the training data. And similarly for the test data. We also have to specify a model name, and here it's important that sorry, that's in the next step. We can pick any model name we want. So we are using the property holding the embeddings from the last step. And here are some kind of standard machine learning parameters, like if we want to do cross-validation, which this is doing, this is the number of folds. And why do we do cross-validation? Well, because we can here enter several model configurations, link prediction model configurations. And what will happen is that this will perform a cross-validation on the train set to evaluate automatically which of these all model configurations is the best one. The best one will then be retrained and evaluated on the test set. So in this case, we try all the three available link feature combiners, which Alicia explained. We set max epochs just so it doesn't train forever, and we try some different penalty values. This is mostly an example. The negative class weight I just set to the most simple value. Let's not overcomplicate. Concurrency is important if you want to make it run faster. And what we get out of this whole business is lots of information about the model. And here we will just look at a few things in the model. So we look at the test score and the train score, which is this area under the precision recall curve. So 1 is the best possible value, 0 is the worst possible. I don't think you will get 0. So we also get to see which model was actually the best one. So, and when we have run this, this model with name model is in a model catalog and can now be used, which we will do. So next step, we will run the link prediction model with the predict procedure in mutate mode. We run it on the same graph, use the same model, and we get a new relationship type. It doesn't matter so much what you call it here, but you will get a new type. We also have to say how many of the best or the most certain predictions do we want to write into this graph or mutate. We can also set the threshold, which means throw away predictions which have a score below this threshold. So yes, let's just run it. And this is one of the steps that Alicia also told you that it can be intensive, especially when the graph grows, because if you have n nodes, then there are roughly n squared number of pairs. But this wasn't a big graph, so we are happy, and we have 200 relationships. The reason it's 200 is because the graph is undirected, so you get both directions, but it's really 100 distinct edges. So it looks like we have a decent model. By the way, the score of 93 is on par with current graph neural networks, and I believe it's close to the state of art. So FastRP is quite interesting algorithm. But we still want to run this model and kind of inspect the results somehow and see if they make sense. So in the last step of this example, we will look at our links and what probability the model gave to them. So in this data set, there is also kind of an answer property that is called subject, and each paper in the data set has one of the following subjects. So they're all super interesting subjects since they're about machine learning, and we like that. So let's just run this cipher magic. And here we have something. So what we notice here is that all of these probabilities actually have the same value. And that can probably be explained if you go into the details of the fast random projection algorithm, but it's not so important. It happens to be like that. But what is interesting is that a lot of these links were actually predicted between papers within the same category. I think there are some exceptions here, but usually, neural network papers like to cite other neural network papers. Here we have, for example, a cross-subject citation. And if we would predict more than top 100, the score would eventually drop here. All right, so we have another example, and that, I think, is a fun one. So this is a social network. We all know about social networks. And although this one is a fake one, it's synthetic, which means we just wrote the script and made up the rules of how people connect. So it's a simple model where there are a set number of communities, and people belong to one random community, and then people within the same community in each time step have a certain probability of connecting with each other. So that's how in this toy example, that's how the social graph will evolve. So let's first just run some simple queries to see what this looks like. There are 5,000 person nodes, and we can also count the train edges. So this I should mention that here we will not use the split relationships procedure. We'll rather, this was done already manually in Python to generate the train, all of these edges by this custom logic. So there are about 10,000 train, we just call them train because we'll use them as the train set. So there are kind of connections between the people. So it's really a connection, not a train thing, but there are also about 10,000 connections which we consider the test set. And finally, we have 10,000 connections which we consider the feature network. And there are only 3 times here, so that you can see it as it represents 3 epochs of time. So first comes the features, then the train, and finally the test. You always test on the most recent data. So when we create this one, we have connected, that's all people that are connected, train, test, and features. All of them are undirected, and it's important that these 2, train and test, have a relationship property, which is called label, and it has two values, 0 or 1, which encodes if it's a positive edge or a negative edge. So yes. Okay, so here we have the graph, and yeah, now it's kind of less work since we did a lot of it in Python. And this step is interesting. So we run the embedding, which is again is fast RP. Let's see if it, did I click it? Okay. Yes. So one interesting thing is, as Alicia said, it's generally tricky to get this pipeline of models right. And the first try, the model was utterly random. And it turns out that if you increase the number of iterations here a lot, then it improved. We'll see that in the next step. But the reason is that if you imagine there are some people in the same community, if you only look at the direct neighbors, you don't get a very good sense of who is in the community. But if you walk up to 10 steps, then you will probably see most people in the community. And why there are zeros first, that's common to do, but it's basically, if this is at, say, iteration 12, it doesn't mean you only get people at distance 12, you get up to 12, basically. So now we have our features, which are the embeddings. So now we can, again, go ahead and train a link prediction model. And let's look at the code here. Right. Sorry about the lag. So it's very similar again to the previous example, only that we picked a bit fewer models here, changed the batch size because that helped a little bit, reduced it from 100, which is default. By the way, L2 is the default of these three. And yeah, it's a similar query. So let's see if it did finish after 14 seconds here, but yeah, we had concurrency 16. And the score is about 70. And this is kind of interesting. Is 70 good or bad? And it's, well, it's not a completely straightforward metric, and it's also very dependent on what problem is being solved. So if you are suggesting friends on a social network, then it's maybe doesn't matter so much. Or if you're a bank and there is a lot of money at stake, even a small improvement can be good. So I think this is decent. And let's see if we can just finish by quickly inspecting the results to see if they make sense. Oops. Probability, did I call it something else? I wonder if I misspelled it. Okay, this is probably, I think this won't work now. Okay, that's embarrassing. Okay, so what I wanted to show you is that if we count how many of the predicted links go to, from the same community, the result was 43 out of 100. So if you would have a social network and you get 100 friend recommendations, 43 are good, then I would say it's at least somewhat valuable. So I think I'll end at that. I think we're out of time. And thank you very much for listening.